Hello students, do you remember studying polynomials in your earlier classes? Let's say you are in a rectangular park and you have to calculate its area. Its length is x plus 10 and breadth is x. What is going to be its area? Now we know that the area of a rectangle is length into breadth. So the area of the park is x into x plus 10, which is equal to x square plus 10x. This expression that you have obtained as an area is a polynomial. In earlier classes, you studied polynomials in one variable and their degrees. Like 4x plus 2 is a polynomial in x of degree 1 and 2y square minus 3y plus 4 is a polynomial in y of degree 2. In this video, you will learn about the different types of polynomials on the basis of their degree, zeros of the polynomial, and geometrical meaning of the zeros of a polynomial. Now students, look at these expressions on the screen. Are any of these expressions a polynomial? No, none of these expressions is a polynomial. It is because they do not fit the rules of polynomials. Polynomials are made up of terms that involve variables raised to the powers which are whole numbers, that is 0, 1, 2 and so on, multiplied by their coefficients and added or subtracted together. Since the degree of these expressions are not whole numbers, they are not polynomials. Let's learn something more about polynomials. Do you know how polynomials are named on the basis of their degree? Let's see. A polynomial of degree 1 is called a linear polynomial. For example, 2x minus 3 root 3x plus 5, x minus 2 by 11, etc. are all linear polynomials. A polynomial of degree 2 is called a quadratic polynomial. The name quadratic has been derived from the word quadrate, which means square. 2x square plus 3x minus 2 by 5, y square minus 2, 2 minus x square plus root 3x are some examples of quadratic polynomials. More generally, a quadratic polynomial in x is of the form ax square plus bx plus c, where the highest power of x is 2, where a, b, c are real numbers and a is not equal to 0. Now, a polynomial of degree 3 is called a cubic polynomial. Some examples of cubic polynomials are x cube minus 8, root 2x cube, x cube minus 2x square plus x minus 1. The most general form of a cubic polynomial is ax cube plus bx square plus cx plus d, where the highest power of x is 3, where a, b, c, d are real numbers and a is not equal to 0. Now students, in class 9, you learned that if k is a zero of a polynomial px equals ax plus b, then putting x equal to k, we get p of k is equal to 0, which means ak plus b equals 0. So after solving for k, you get k is equal to minus b by a. Therefore, the zero of the linear polynomial ax plus b is minus b by a, which is equal to minus of the constant term upon the coefficient of x. Thus, the zero of a polynomial is related to its coefficients. Does this happen in the case of other polynomials too? For example, are the zeros of a quadratic polynomial also related to its coefficients? we shall discuss these points through their geometrical representation. You know that a real number k is a zero of the polynomial px if p of k is equal to 0. But why are the zeros of the polynomial so important? To answer this, first we will see the geometrical representations of linear and quadratic polynomials and their geometrical meaning of their zeros. Let's begin. For a linear polynomial ax plus b, where a is not equal to 0, the graph of y is equal to ax plus b is a straight line which intersects the x-axis at exactly one point, that is, minus b by a. Therefore, the linear polynomial ax plus b, where a is not equal to 0, has exactly one zero, which is minus b by a. For example, consider the linear polynomial y equals 2x plus 1. We can represent this polynomial geometrically by plotting its graph on a Cartesian coordinate system. To do this, we assign values to x and calculate the corresponding values of y. Let's see. For x equals minus 2, we get y equals to 2x plus 1, which is equal to 2 into minus 2 plus 1, which is minus 3. For x equal to 0, y equals 2x plus 1, which is equal to 2 into 0 plus 1, that is 1. Plotting these points, that is minus 2, minus 3 and 0, 1 on the graph and making a line through them, we can see that the polynomial 2x plus 1 intersects the x-axis at minus 1 by 2. Thus, the zero of the polynomial 2x plus 1 is minus 1 by 2 because the zero of a polynomial is the x-coordinate of the point where the graph of y equals 2x plus 1 intersects the x-axis. In general, for a linear polynomial ax plus b, where a is not equal to 0, the graph of y equals ax plus b is a straight line which intersects the x-axis at one point, minus b by a, 0. Therefore, it has exactly 1, 0, which is its point of intersection at the x-axis. Now that we've explored the geometric representation of a linear polynomial, let's move on and discuss it for quadratic polynomials. Consider the quadratic polynomial x square minus 3x minus 4. Let us see what the graph of y equals x square minus 3x minus 4 looks like. To do so, we shall list a few values of this polynomial by assuming a few values of x and getting values of y. For x equals minus 2, we get y equals x square minus 3x minus 4, which is equal to minus 2 square minus 3 into minus 2 minus 4, which is equal to 6. Similarly, taking other values of x as minus 1, 0, 1, 2, 3, 4, 5, we get y as 0, minus 4, minus 6, minus 6, minus 4, 0 and 6 respectively. If we locate the points listed on a graph paper and draw through these points, it will actually look like a curve. So, for any quadratic polynomial ax square plus bx plus c, where a is not equal to 0, the graph corresponding to the equation has one of the two shapes. It's either this or this. depending on whether a is greater than 0 or less than 0. These curves that we obtained are called parabolas. So for any quadratic polynomial ax square plus bx plus c, where a is not equal to 0, the zeros of the polynomial are precisely the x-coordinates of the points where the parabola intersects the x-axis. Now, as mentioned, the shape of the graph y equals ax square plus bx plus c depends on the value of a. The shape of the graph can have three cases. Let's discuss them one by one. Case 1. The graph cuts x-axis at two distinct points, at a and a dash. This means the polynomial has two zeros, a and a dash. Moving on, we shall discuss case 2. In this case, the graph cuts the x-axis at exactly one point, or we can say at two coincident points. Here, the points a and a dash of case 1 coincide to become one point a. Next, we talk about case 3. In this case, the graph is either completely above the x-axis or completely below the x-axis. It does not cut the x-axis at any point. The polynomial has no zero in this case, as at no given point the parabola intersects the x-axis. Now students, what do you expect the geometrical meaning of the zeros of a cubic polynomial to be? Let us find out. Consider a cubic polynomial x cubed minus 4x. We shall list a few values of y corresponding to a few values of x that we assume. For x equals minus 2, we get y equals x cubed minus 4x, which is equal to cube of minus 2 minus 4 into minus 2, which is equal to minus 8 plus 8, which is 0. Similarly, taking values of x as minus 1, 0, 1 and 2, we get y as 3, 0, minus 3 and 0 respectively. If we locate the points listed on a graph paper and draw through them, it will actually look like the curve on the screen. The curve intersects the x-axis at minus 2, 0 and 2. This means that there are three zeros of the polynomial. Always remember that any polynomial of degree 3 can have at most 3 zeros. Now students, from all these examples, we learn one thing common. That is, if a polynomial px is of the degree n, then its curve will intersect the x-axis at most n points. Therefore, a polynomial px of degree n has at most n zeros. So students, with this, we have come to the end of this video. Now that you've understood the topics, open the EduRev app, study the chapter notes and take the test of this chapter. Your marks are going to tell you whether you've understood the topic. Also, here's an amazing secret. You get video lectures, chapter notes and MCQ tests for all the chapters in the EduRev app. That's the magic of EduRev courses. You get everything in a single place. And not just mathematics, you get amazing courses for social studies, science, English, Hindi and much more on EduRev. Thank you.